Welcome again to the new sessions. In the last class, we discussed about the subspace and proved some results for a subspace. We solve the intersection of two subspaces again is a subspace, and we show that the union of a two subspace need not be a subspace, and also discuss the sum of the two subspaces is again subspaces. Okay, today's class we discuss about the linear spin, and so we can start linear spin. First, we start with the linear combinations. Linear combinations means we simply say that if we have a vectors v1, v2, vn in a suppose v1, v2 up to finite set vn in a vector space v. Then the combination of this can be expressed in the form of this alpha 1 v1 plus alpha 2 v2 and so on plus alpha n vn. If these vectors v1 v2 any vectors in a vector space can be expressed in the form of a this is called is a linear combinations of the vectors of a v1 v2 vn, where alpha 1 alpha 2 alpha 3 and r are called the scalars, is a coefficients of the real coefficient. So this means we can say that let v1 v2 vn be a vectors in v if any vector v can be expressed as a form of a alpha 1 v2 this thing. We can just say that we take a arbitrary vector. This can be choose any arbitrary vector from the vector space v, and if this vector can be written as a in this form alpha 1 v1 plus alpha 2 v2 means written as a combination of all these vectors v1 v2 vn, where alpha 1 alpha 2 alpha n are the scalars, then we say that this vector v is a linear combination of the vectors of a v1 v2 vn. So this means we can say that into this form. These scalars alpha 1 alpha 2 and r are the coefficients of the linear combination. We move to the another vector v1 v2 v3. We have this. So we have three vectors are there. Then we can just check this. You can write we can write 1 3 1 can be written as a 0 1 2 plus you have a 1 0 minus 5. Now if you take a, we can write in the form of a this is we can write in the form of a this is equal to 1. If we take a this is equal to we take is equal to 3. If you take this is nothing but is can be written as a 0 3 and 2 plus is equal to 1 0 minus 5, and this can be written as a 0 plus 1 3 plus 0. This is sorry, this is equal to you have a 6, and then we have a 6 minus 5, and this is nothing but is equal to 1 3 1. So we can just say that this means we can say that v1 can be written as a 3 times of a v2 plus v3. That means we choose a one vector. This vector can be written as a linear combination of these two vectors. So we can say that we choose a when vector this can be written as a linear combination of these two vectors. Okay, so this way we can just say that into this form. Vector this as a linear combination of this or not, we just try. Can we write this is written in the form of this? So we can write alpha times of a 1 comma 0 plus beta times we can say that 0 into 1. This can be written as a alpha 0 plus beta times 0 1. This can be written as a alpha beta, and now we equating this alpha is equal to 3 and we have a beta is equal to 4. So this means 3 comma 4 can be written as a linear combination of this vector 1 0 plus 4 into 0 1. So this means this vector can be written as a linear combination of these two vectors. So easily we can explain this. So this means we can write any vectors can be written in the linear combination of two vectors into this form. Okay, so now we to start with the new example. This is a different type of example we have to show, not ordinary. In this we define a vector space addition and scalar multiplication in a different way, not the ordinary addition and scalar multiplications. R2 x1 x2 we have a such define the addition x1 x2 y1 y2 in this form x1 plus y1 minus 2 and x2 plus y2 plus 3. and scalar multiplication alpha x1 plus alpha x2 is can be written in the form of a we write in the form of a minus 2, alpha x1 minus 2 alpha plus 2 alpha x2 plus 3 alpha minus 2. So now the question is this: is 110 is a linear combination of these two vectors or not? So if we assuming that 110 can be written in the linear combination of these two, means we can say that 1 0 can be written as a alpha times of a 2 3 plus beta times of a 1 comma 4, where alpha beta are the some real number, where alpha and beta are the some real number. So now we have to try to find the values of alpha and beta, which is giving to the this combination can be written is equal to 110. So just because we have to take a scalar multiplication, 2 into alpha times 2 into 3, when scalar multiplication is defined into this form. So we have alpha x1 minus 2 alpha plus 2. So alpha x1 is equal to 2 and x2 is equal to 3. So this can be written as a alpha, then it's 2 alpha minus 2 alpha plus 2, and then we have to 3 x2 is equal to 3. So we have a 3 alpha plus 3 alpha minus 3. Similar fashion we can calculate as a beta of 1 comma 4. So x1 is equal to 1, x2 is equal to we have a 4. So we can write is equal to you have a beta minus 2 beta plus 2, and then we have a x2 is equal to 4. So alpha in alpha plus beta. So we have a 4 beta plus 3 alpha minus 3. So this can be, we have to simplify this 2 we cancel out, this is equal to 2 comma 3 plus 6 alpha minus 3, and this can be written as a you have a minus beta plus 2, and then 4 and 7 this is beta. So this is beta, so 7 beta minus 3. So we have a now we take a this quantity and this quantity, we can write the sum of these two terms, because these two terms will be we can write in the form of this. So we can write is a 2 times of a, we can write as a this is equal to, we can write so alpha times of a 1 comma 10 is equal to alpha times of a 2 3 plus beta times of a 1 4. We calculate the value of this. We have to writing this is equal to 2 times of a 6 alpha minus 3, and we calculating this is equal to minus beta plus 2, and we have a 7 beta minus 3. Now addition, we have to, you know that addition of these two vectors we define x1 and we have a addition is defined in this way: x1 x2 plus y1 y2 is equal to x1 plus y1 minus 2, and we have a x2 plus y2 plus 3 plus 3. Okay, so that means this we can just write into this: x1 is equal to 2, x2 is equal to this is y1 and this is y2. So this is we can write in the form of x1 plus x2. So 2 plus minus beta plus 2 minus 2, and then we have a x2, we have a 6 alpha minus 3, y2 plus 7 beta minus 3, and then we have a plus 3. So this can be written in the form of you have a 2 minus beta, and this can be written as you have a 6 alpha plus 7 beta, and you have a minus 3. Now equating these two this equal, so we can say that 2 minus beta is equal to 1, and we have a 6 alpha plus 7 beta is equal to 3, and now this is 2 minus beta, it means beta is equal to you have a 2 minus 1 is equal to 1. So we have a beta is equal to 1. This implies that we have a 6 alpha is equal to we have a we can write into form this is equal to you have a, so we have a 6 alpha plus 7 beta minus 3 is equal to 10. So this implies that we have a 6 alpha plus 7 beta is equal to 13, and alpha here we have a beta is equal to 1. So we can write 6 alpha is equal to 13 minus 7, and then this means 6 alpha is equal to, you have a 6. This implies that alpha is equal to 1. So we have a find values for alpha and beta is equal to 1. So this means we can say that 1 comma 10 can be written as a 1 into 2 3 plus 1 into 1 4. So this, yes, we have to say that this 1 comma 10 can be written as a linear combination of the elements of a 2 3 and 1 4. So this means clearly you can just verify this. A is equal to 2. First this is alpha times of a x1 and y1 is the form of a alpha x1 plus minus 2 alpha minus 2 alpha plus 2, and you have a alpha of x2 plus 3 alpha minus 3. So 1 into this we can just write in the form of a this can be written in the form of in this form, and this you put this. So this is clearly this can be written in the form of this. So if you put alpha is equal to 1, beta is equal to also 1, then this can be written as a 1 and 10 can be written as a linear combination of these two. Okay, so now we have to again one more questions. In this we just try to take polynomials of degree less than or equal to 2, and we have a v1 v2 v3 be the vectors in p2. Then this polynomials is a linear combination of this. So if this is a linear combination of this means we have a 7 square minus 15. So minus 15 can be written as a alpha times of a v1 is equal to x square minus 1 plus beta times of a v2 we have a x square plus 3x minus 5 and plus gamma times we have a x v3. So this can be written as a, we have to compare the coefficient of x square and all these things. So we have a alpha plus beta x square, then we have a 3 beta plus gamma x, plus we have a constant term. We have a constant term is equal to, you have a minus alpha minus 5 beta. Now equating this we have a equal coefficient powers of a x. So we have a alpha plus beta is equal to 7, and we have a 3 alpha plus gamma is equal to, we have a 0, and we have a minus alpha minus 5 beta is equal to minus 15, and this can be written as alpha plus 5 beta is equal to 15. So we have a alpha plus beta is equal to 7 and alpha plus 5 beta is equal to 15. Now we have to subtracting this, so we have to cancel this. So you have a minus 4 beta is equal to, you have a minus 8. So beta is equal to, you have a beta is equal to, you have a 2. So we have a beta is equal to, clearly is equal to 2, and if beta is equal to 2, then we can say that calculate the alpha. So from alpha plus beta is equal to 7. So we can say that we can write as the form of a, so we have a alpha, so beta is equal to, we have a 2, and alpha plus beta we have a alpha plus beta is equal to, we have a 7. So we can say that alpha is equal to, you have a 7 minus beta. So we have a alpha is equal to 7 minus beta, in which 7 minus 2 is equal to 5. So alpha is equal to, you have a 5, and then also you have a 3 alpha plus gamma is equal to 0. You have a 3 alpha plus gamma is equal to 0. So 3 alpha plus gamma is equal to 0. So this means we can say that we can write in the form of this. So we have a alpha plus beta. So we have a alpha, sorry, 3 beta plus, so not alpha, 3 beta plus gamma is equal to 0. Beta is equal to 2. So gamma is equal to minus 3 beta. So gamma is equal to minus 6. So that's why we can say that 7 x square minus 15 can be written as the form of alpha is equal to, you have a 5 times x square minus 1, beta is equal to, you have a 2 times you have a x square plus 3x minus 5, and then you have a plus gamma is equal to, you have a minus 6 times of a x. So now we have a clearly 3 to the 6 x is cancel out. So we have a clearly is written in this form. We have to in this form simply. Okay, so now we move to the span. Span is nothing but is equal to, we have a S, a non-empty subset of a vector space V, and the span of this set S is the set of all possible linear combinations of the vectors in S, and then means denoted by span of S. If we have a S is a V1, V2, Vn vectors, then span of S nothing but all possible finite linear combination of this in the form of alpha 1 V1 plus alpha 2 V2. So this where alpha I is the element of a real and I lies between 1 to n. So in simply say that span of S nothing but is equal to V collection of all the linear combination of the vectors V1, V2. So all possible linear combination of the vectors V1, V2, Vn is belong to the span of S. So if any vectors belongs to the span of S, let's suppose we can say that V is the element of a span of S. That means V can be written as a finite linear combination of the elements of S. This means V can be written as a alpha 1 V1, alpha 2 V2, and so on plus alpha n Vn. So that means this is the one. If we have another vector, suppose U is the belong to the span of S, then U can also written as a finite linear combination of this. Suppose beta 1 V1 plus some another different beta 2 V2 plus so on. We have a plus beta n and Vn, where you have alpha i's and beta i's are the element of a R. All are the real numbers. So in this case we can say that means span of a set is nothing but span of a set is the collection of all the linear combinations of the vectors V1, V2, Vn. Okay, for example, for a subset 0 and 1, we try to because we take a V is the element of a R2, and V is R2 means V is the element of the form because all the element of a R2 is R2 means we have this is clearly the vector space is the form of a xy, and xy is the element of a R over a field of a real number. In the beginning we already said that the throughout this course we assuming that our field is real, otherwise specify a different field we have to use. So if R2 is equal to this means V is the form of some x and y. So if we have to find for a subset span of S, means span of S what the element of belong to the span of S, we take a suppose x and y. It can be written as a 1 0 plus beta times 0 and 1. So we try to find a span of span of if V belongs to the if V is the element of a span of S, then V can be written as a finite linear combination of the vectors of this. So V can be written in the form of this form, and then we can write this is nothing but is equal to alpha and beta. So this means span of S is nothing but is equal to of the form of a alpha beta, such that alpha and beta are the real number, and this is nothing but is equal to whole R2. So this means we can find, so we just say that if any set we can find it is belongs to the span or not, we can write if this particular arbitrary element from belong to this vector space, it is possible we can find this vector space can be written as a finite linear combination of the vectors of a V1, V2 and so on. This we have is R2, we have a V1 and V2. So that's means this is equal to R2. Now we have to find the span of S. In this case, suppose V3, V is equal to R3. So this means suppose we have to take a V is the any arbitrary element belong to the span of S. That means this V can be written as a alpha 1 V1 plus alpha 2 V2. And then because we have only two vectors are there, so this means this can be written as a alpha 1 times 1 0 0 plus alpha 2 times 0 1 0, and this is nothing but is equal to alpha 1 0 0 plus 0 alpha 2 0, and this is can be written in the form of alpha 1 alpha 2 and 0. So this means span of this S is nothing but is equal to all the element of a alpha 1 alpha 2 such that alpha 1 alpha 2 are the element of a R, and this is nothing but is equal to, you have to just say that xy plane, and but initially we have a xyz plane vector space is there. So span of S is the form of a alpha 1 comma alpha 2 and 0, third element is equal to 0. Now we just take a span of this can be written into this form. So we can write into this form. So now the question, we just say that I just said span of S we write in the form of a alpha beta comma 0 such that alpha and beta are the element of, or alpha 1 beta 1 is not a problem, we have all the real number. Now the question is, do this belong to this? Yes, this is belong to this because we take alpha is equal to 3, beta is equal to 2. So this is clearly 3 and 2 comma 0 is the belong to the span of S. So this can be written as a finite linear combination of this. Why? This can be written as a finite linear combination of the form of this vectors. So you have a 3 times 1 0 0 plus 2 times 0 1 0. So this can be written as a linear combination of this. So this seems belongs to the span of this, but 2 5 1 does not belong to the span of S. Why? Because the span of S is the form of a last element should be the 0, but here is a 1. So this is cannot possible, that means this is belong to the span of S. So that means we can say that 2 5 1 is does not belong to the span, but 3 2 0 is belong to the span of S. Now my question is again, is this span of S is a subspace of a R3 or not? What is span of S? Span of S we have a in the form of a we take a for the moment in place of a this we can is the form of this x y 0 such that x and y are the element of a R. This is the span of S. So if we show that this span of S is a subspace or not, so we use the subspace theorem, and the subspace theorem is say that we have to first check is 0 is belong to the this or not. Yes, truly 0 0 0 is the belong to the span of S. This means 0 0 can be written as a linear combination of this. So 0 0 0 can be written as a 0 into 1 0 0 plus 0 into 0 1 0. So this is not a problem. So now next is to show that if we take a two arbitrary element belong to the span of S, then we show that there are some is also belong to the span of S. If U belong to the span of S, then U can be written as a linear combination of the elements of a x, y, 0, and V can be also written, if V belong to the span of S, then V can also written as a some beta times x, y, 0 types element. And now because of this U and V, so we take a U plus V can be written as a this is nothing but is equal to by this scalar multiplication alpha x alpha y 0 and plus beta x beta y 0, and this is nothing but is equal to written as a alpha plus beta x alpha plus beta y plus 0. Alpha and beta are the some real number. We take a alpha and beta are the some real number. Sum of a two real numbers is again is a real number. This is R. This is again is R. So this means we can say that this can be written as some this is the form of some real number x and some real number gamma y comma 0, and then this is x is also is a because this is a real number. So this x and y are the real number. So this is the belong to the this whole thing is belongs to the R, and this is whole thing is belongs to the R. This is the belong to the span of S. So this means span of S is clearly closed under the under addition, and trivially we can say that alpha times of we can say that this u. So alpha u can be written as a, we can just say alpha times v. So we take alpha v. So alpha times of we have a beta x beta y 0, and this can be written as alpha beta x alpha beta y comma 0, and this is all belongs to the R. This also belongs to the R. So this is element of a some elements x comma y comma 0, and this is clearly belong to the span of S. So this implies that we can say that alpha V is also the belong to the span of S. So in this case we can say that all the three properties of this subspace theorem is satisfied. Span of S0 0 belong to the span of S. If we have a sum of a two element of the span of S is again belong to the span of S, this is closed under addition and also closed under scalar multiplication. So that means we can say that span of S is a subspace of a R3. Okay, so now I just go to one more example in the related to the 2 by 2 matrices over reals. So consider the matrix A, B, C. Now determine whether D is in the span of this. So if D is the span of this, means D can be written as a alpha A plus beta B plus gamma C. So D can be written in this form. If D belongs to the span of this, so D is the belong to the span of A, B, C, then D can be written as a finite linear combination of the elements of A, B, C. If D written in this form, this means case as A we have a 1, minus 1, 1 and 2, plus we have a beta times 0, 2, 0, minus 1, plus gamma times 0, 1, 5, 2. If we find two elements of alpha beta in such a way which satisfy this equal to giving to D, then we can say that this is satisfy this condition truly, and this is nothing but this can be written the alpha minus alpha, alpha and 2 alpha plus 0, 0, 2 beta minus beta, and plus you have a 0, gamma, 5 gamma and 2 gamma. So first we can just say that alpha plus, and that right hand side, left hand side we have a 1, 2, minus 4 and minus 2. So this can be written in the form of this. We have a alpha plus 0 is alpha. So you have a next is a minus alpha plus 2 beta plus gamma, and now we have a alpha plus 5 gamma. We have a 2 alpha minus beta plus 2 gamma. So here alpha is equal to, we have a clearly see that we have a alpha is equal to 1, and now we have a minus alpha plus 2 beta plus gamma. So we have a minus alpha plus 2 beta plus gamma is equal to, we have a 2, and now we have a alpha plus 5 gamma. So you have a alpha plus 5 gamma, we have a is equal to minus 4. Then we have a 2 alpha minus beta. So we have a 2 alpha minus beta plus 2 gamma is equal to, you have a minus 2. So we have a alpha is equal to 1. So if alpha is equal to 1, so we have a 5 gamma is equal to minus 5. So gamma is equal to minus 1. And then we have a alpha is equal to 1, gamma is equal to minus 1. So we just write anywhere is this. So you have a 2 beta is equal to, you have a 2 plus alpha minus gamma. So you have a 2, alpha is equal to plus 1, and then you have a plus 1 is equal to, you have a 4. So beta is equal to, you have a 2. So we have to find the value for alpha is equal to, you have a 1, beta is equal to 2, and gamma is equal to, you have a clearly is equal to minus 1. So that means we find that this is can be written in the form of this. So this means we can say that this 1, 2, minus 4, 2. So 1, 2, minus 4, minus 2, and then is equal to can be written in the form of a 1 into 1, 1 into 1 minus 1 minus 1, 1, 2, and then beta is equal to 2. Then we can write as a 2, 0, 0, 2, and you have a minus 1, and then plus minus 1 times you can write in the form of a 0, 1, 5, 2. Now you can say this is 1 clearly, minus 1 minus 1 is equal to 2, and then you have a this is equal to minus 5 plus 1 is equal to minus 4, and minus 2 plus 2 and this is equal to -2, so this is -2, this is clear. So this means clearly we can write that means this implies that this is equal to 1, 2, -4, -2 belongs to the span of A, B and C. Okay, so now I just say that I end this session with this example. The polynomials 1x x square, this is the span the vector of a Pn, because we have to just show that in P2 case we can say that any 1x and x square can be written as a linear combination of this alpha naught plus, sorry, we just write written in the form of a naught a1x plus a2x square. So in general, if we write the P is equal to this, so this means Pn is nothing but is equal to all finite linear combination. The span of 1 plus x is equal to nothing but is equal to whole Pn. So span of 1, this means this vector can be written as a alpha plus beta and so on, and element of a P is equal to this, alpha naught is equal to a naught, alpha 1 is equal to a1, and so on like this. So this way we can write a spanning set of a Pn is nothing but is equal to all the elements of this P1 to x square up to xn is the spanning set, and this is we can write is this form. P can any arbitrary element choosing this form, this can be written into a this form. So this is the spanning set we write into a this form. Now the question is this, if v1 v2 be two vector spaces and w is equal to span of a v1 and v2 is a subspace of a v or not. So we have a subspace w v1 v2 be in vector space, and w we take w is a form of a span of v1 and v2. So if we show that this is a suppose we take two different elements of this, if clearly 0 belongs to the w. Why? If w is the span of this, so 0 can be written as a 0 into v1 plus 0 into v2. So 0 is the element of a w because 0 can be written as a finite linear combination. So w is a non-empty. This means clearly we can say that this is our set is a span of this. Now we take a two element u and v are the element of a w. So if u can be written as a finite limit alpha 1 v1 plus alpha 2 v2, and v can also be written as a suppose beta 1 v1 plus beta 2 v2, where alpha 1 alpha 2 beta 1 beta 2 are the element of a R. Now we take a u plus v, is can be written in the form of this. We have alpha 1 v1 plus alpha 2 v2 plus beta 1 v1 plus beta 2 v2, because v1 v2 are the vector in vector space. So this is all the properties hold. This can be written as alpha 1 plus beta 1 into v1 plus we have a alpha 2 plus beta 2 v2, and this is nothing but is equal to belongs to the R. This is also belongs to the R, means this can be written as a finite linear combination of this. If this is linear combination of this belongs to the span of v1 and v2, and this implies that we can say that u plus v belongs to the w. So this can be written as a span of finite linear combination, and w is equal to span. So means we can say that w is closed under the addition. Now we take a some alpha u. Alpha u is nothing but is equal to alpha 1 v1 plus alpha 2 v2, and this is the element of a R, and this is also the element of a R because alpha also belongs to the R and alpha 1 alpha 2 belongs to the R. Then the product of two real number is again is a real number, so we can write into this form. Is again is a finite linear combination, is again span of v1 and v2, and this is w. So this we can say that alpha u is also belongs to the w. So that means we can say that this set is again closed under the addition and under the scalar multiplication. So that means we can say that so this means this w span by v1 and v2 is a subspace of a vector space V. Okay, so now I have to stop today's lecture in this question. In the next class, we have to continue with the some properties of a spanning set, and see we have to do some more examples of this. Thank you very much.